Now it's
Do we-
coming. Yes, perfect.
Okay, hold on. Then let me say again. Hi, everybody. This is the webinar by the IEA SHC Solar Academy on the topic of solar hot water for 2030. And as you heard me say, my name is Arabella. I'm with ISIS, and we are the technical host of the event. And I was just about telling you that ISIS has actually been around for quite a while, since the 1950s. And our mission is 100% renewable energy for all, used efficiently and wisely. And to exact this mission, we have quite a lot of activities going on. You will probably heard about our conferences, for example, the Solar World Congress 2025, which is just coming up next week. We have a Eurosun conference that we do every 2 years. We do webinars such as the one today, and we have education initiatives, 2 major publications. One of them is the Solar Energy Journal, which you are probably quite familiar with. And we do infographics, and we even have a solar energy museum. So we are taking the solar very serious here. You guys have joined us for a webinar, and of course, Q&A session is one of the most important parts of that webinar. So we will hear the presentations from our 3 presenters first. While that is going on, you can already submit your questions in writing via the chat box in Zoom. Start sending your questions in anytime throughout the webinar, and please keep them short and precise so we can kind of work with them in an easy way. And we will have a cumulative Q&A session at the end of the event. And with that, I'm actually happy to introduce you to the voice you just heard. That's Bärbel Epp. Bärbel is the founder and managing director of the consultancy Solvico, and she's also responsible for the online blog Solar Thermal World. Bärbel is our host moderator for these events, and well prepared to take in all of your questions. So Bärbel, happy to hand over to you.
Yeah, thank you very much, Arabella. I'm happy to be with you this afternoon, morning, evening, wherever you are in the world. We have actually speakers from all around the world today with us. So they did a big effort in getting up early or staying up late to join us today. So I will give you a brief introduction into what is the Solar Heating and Cooling Program, because we are the organizers of the Solar Academy series of webinars that we host together with ISIS. You see my slides correctly, I hope. Yeah, it's
Not yet, not yet.
Oh, the
Can you
same.
please, yeah, can you please
Wow.
share again?
Right. Okay, let me try again. Then I'll try again.
Yeah,
now we
go.
go. Okay. Yes. Well, yeah, so the Solar Heating and Cooling Program is a research-based collaboration worldwide. We have 19 member countries, which are marked in orange on this map, and we have a number of countries which are member via international organizations, altogether 9 organizations, so that we are covered on all continents, as you see on the red parts of the map. There are more than 200 researchers mainly, but also industry representatives, which join to work on different tasks. This is how we call the research platforms, and they are active in different topics, and I've listed some of them here. Currently, we have one on PVT heating systems. We have thermal energy storage materials, also component for thermal energy storage. Then we have a lighting task, also life cycle and cross assessment for cost assessment, sorry, for heating and cooling technologies. And then a quite new one on solar photoreactors for the production of fuels and chemicals. And then the one which is today spending the time with us on solar hot water for 2030. What is the Solar Academy? It's generally a platform which shares the findings and results from the research work, but be confirmed that it's not only reports that we publish, but we also have training materials, often case studies, fact sheets, databases, and also tools, which are among the deliverables of the different research platforms. Yeah, we have these webinars regularly with ISIS. We have the one today, and then there's another one planned for December 2025. They are also always held on Tuesday in the afternoon and on Thursday morning, so that the different regions of the world can participate. The previous webinars with all their recordings and the presentations are available for download under this link on our website. And I want to stress the fact that we offer on-site training. This must be on the request of an IEA SHC member country organization, and the previous ones were in China, Cape Verde, West Africa, United Kingdom, and South Africa. If you want to have further information, join the website or look into this particular rubric on the website, which is publications. There you find all the latest reports and also a filter function. Then we are on LinkedIn and YouTube. And if you have particular questions, you can contact the Secretariat. There are two key publications that I want to mention here. This is the Solar Heat Worldwide study, which is published once a year on an annual basis, last time in June 2025, and it's the most comprehensive national, regional, and global data resource on solar heating and cooling markets. And then there is Solar Update, which is like a newsletter type of thing, which covers latest news from the tasks and is published regularly on a more or less 6 monthly basis. So this brings me to the webinar today, and I want to introduce our first speaker. We have two professors here today with us, and one is Professor Robert Taylor from Australia. He has served as an academic at the University of New South Wales, Australia, since 2011. His main research interest is in the development of next-generation solar thermal energy systems. He is researching novel components, fluids, materials, and systems to increase the utilization of solar energy in society. Professor Taylor has published over 300 academic outcomes. And he will introduce now to the task 69 and will give us an overview on coming up deliverables. So, Robert, the floor is yours. I'm looking forward to your presentation and stop my sharing.
All right, thank you for the introduction, Berbel. Let me please confirm if my screen is sharing, because it seems it's not so straightforward.
Well, it's sharing, but not in presenter mode yet. But you will get this sorted out. Perfect. Super.
Okay. All right. Yeah, welcome everybody to this Solar Academy, and thanks again for the introduction. So I'm one of two task managers. My colleague, Professor Hertao from China, and I have been managing this task, Solar Hot Water for 2030, for the last 3 years and a bit. We actually got a small extension until the end of the year to finish up some of the work that's been going on in the task. And yeah, I'm just going to give a brief overview into the task and maybe touch on a few of the things that we're doing that aren't related to the other, don't want to steal the other two speakers' thunder for later. So I'll just give a little bit of an overview. So the reason that we decided to start this task is that water heating is actually a pretty big portion of the primary energy use globally. And in some locations around the world, in the residential building, it can be up to 50% of a building's energy demand. And so it's something that we can't forget about whenever we're thinking about trying to get to kind of like net zero society. And if we can provide that hot water heating with solar energy, then we can avoid some of the nasty impacts that might happen from climate change. And so if we wait until later and later and later to start dealing with this problem, I've got the little kind of asteroid running into the Earth picture there. The sooner that we can take action, the easier it is, and the easier it is to change the trajectory. And as we've gone along in the task, we've realized that solar hot water has a lot of interesting applications, particularly whenever you start thinking about using photovoltaics to make hot water. There's some interesting interactions with other things, like whenever you get to really high levels of photovoltaics on the grid, hot water is an interesting opportunity for, basically storing excess PV electricity during the middle of the day and making sure that it gets used rather than curtailed and turned off. Another part of the motivation is, and the reason that we picked 2030, I guess, as the kind of target deadline for us, it's pretty near term. And there was an IEA report that said if we want to get to net zero by 2050, we need to have something like 400 million dwellings around the world with solar thermal on the rooftop. And business as usual, unfortunately, for solar thermal technologies is starting to slow down a bit. And so we thought, well, if now could be a good time to have a task, this is back a couple years ago, to try to fill that gap and kind of re-accelerate the solar thermal and solar PV as well for hot water technologies. And also at the same time, there's a lot of targets, national targets and international targets that kind of had something around 2030. So that's how we got going on this task. And basically the task focuses on two technologies. Of course, there's a few other options, but two technologies which we thought, and I still think are quite viable for now and into the future. One is thermosiphons, where you don't need any pumps. So you rely on the sun warming the water to kind of pump the liquid. Basically, you get the density change of warming up water, circulates the water through the system. And right now, that's basically the dominant type of solar hot water technology in the world. Somewhere greater than 50% of systems are thermosiphons. And also PV hot water systems, which actually I'm sure we'll discuss in one of the talks later, comes in all shapes and sizes, but is growing very fast. And an interesting thing about PV hot water is it used to be a ridiculous idea to take your $100 a watt photovoltaic system and turn it into something as simple as hot water. But now that PV is getting so cheap, it's, in a lot of places now you can install a system for much, much less than $1 per watt. It's starting to make a little bit of sense. And if you pair it with a heat pump or something, you can get back to similar efficiency as a thermosiphon. So both of these technologies were of big interest to us, and they have some similarities that they don't require a lot of moving parts. They can now both be pretty affordable and reliable, and there's some interesting opportunities that might interest manufacturers to try to get some new products, components, smart systems, things like that, which I think will be discussed later as well a little bit. And then whenever you think about where are these kind of solar systems being installed, well, we've seen a little bit of a decline in the market in China, which used to be definitely the leader. But there's still quite a bit of growth for solar hot water in sub-Saharan Africa and in other parts of Asia. People are always going to need hot water. So anyone that's tried to take a cold shower will very much appreciate having some hot water in your house. But in terms of the solar technologies installation, there's a few key growth areas out there, and a few of the historic ones are slowing down a bit. Just looking at what was installed recently, I guess this is a little bit older, but some data from the Solar Heat Worldwide report shows that same picture, that thermosiphons, so the bottom blue bars of this little bar chart here, are dominant in Latin America, Sub-Saharan Africa, and Asia, excluding China. And there's a little picture there from a recent trip that we took part of the task to Namibia, where there's thermosiphon systems being installed. In some of the other markets around the world, I'm not sure where everyone is joining from, pump systems can be more popular. And that works well, of course, if you have a reliable grid where you can use electricity for pumping the water. But places where maybe there isn't such a reliable grid or where there's a lot of rural areas, thermosiphons are a good solution. But another technology that's starting to come in there, and I just drew little red bars there, is the PV hot water technologies. And PV hot water can also work in places where there isn't a reliable grid, because PV can be off grid, and they have, we'll talk about it later in the next presentation, but there are ways to just have the PV dedicated to making hot water. And also in places where there's a lot of PV on the grid already, like where I'm coming from here in Australia, there's places where the electricity price can go negative because we have too much PV in the summertime during the middle of the day. And you can actually get paid to take electricity off the grid because there's so much solar. And so those places, those parts of the world are starting to see some growth. Right now, it's very small. I mean, it's little bars there, but I think that's a technology that's going to grow a lot in the future, next few years. So just a few other little points that were in the task that I think are interesting that are worth discussing is one of the things that's ongoing, just recently got some live data from, is a comparison study at the Namibia Energy Institute, where they're looking at a PV hot water system, a flat plate thermosiphon system, and an evacuated tube thermosiphon system, all in the same location, all with similar energy outputs, same storage tank area, and they're just now getting some live data from that. So it's kind of a nice experimental study that I was actually on the ground visiting last month in Namibia. We also had a bit of work on standards inside the task. So there was a new Chinese standard, which you can see there, and we had a report on different standards and certifications from around the world, which is published on the task website if anybody's interested. But there's quite a few configurations and quite a few standards around the world, and they don't always capture everything, and they don't always line up. So there's some recommendations in that report about harmonizing standards and certifications. Also in the task, we've done a little bit of training sessions and looked at some of the needs for training. So we had some in-person trainings, and of course this sort of Solar Academy sort of counts as a bit of training. And we had a training session in China, and we had a training session just recently on that visit to Namibia. In terms of what is needed for training, we did at both of those places, we asked participants what they want to see more of in terms of training. And the top two things that came up was installation and commissioning of new solar hot water systems, which is covered quite well, I guess, with some of the work that's associated with our task, but predated us, which is the Soul Train project, Soul Train Plus. I don't know if anyone's heard of that, but that's got a lot of training inside of it. And the design and installation of heat pump systems was also another interesting thing. So the heat pumps, of course, go very well with these PV systems. So anyway, that's just some tabular data about what people wanted to see in the future. So that's a little bit of future work, I guess, coming from the task. And overall, I learned a lot during this task. We have a few more months to go to get our final deliverables. But one thing that I've found to be interesting is that it really brought together a lot of people from a lot of different cultures, perspectives, different climates, different kinds of markets. And solar hot water, I think, has a role to play, maybe different technologies, different configurations, but all around the world. There's a demand for it and a way that it can be made to work, I think, economically and technically in all over the world. And of course, running this task, I had opportunities to visit experts in all over the world, and we had some really nice meetings all around the world. And another interesting thing about solar hot water is you might think, oh, that technology has been around for 20, 30 years. And in fact, solar hot water predated PV. Probably there was more installed systems of solar hot water before there was any PV installed, just because it was so expensive for so long. But there's still a lot of innovation happening. So there's a lot of new configurations, smart systems, control systems, assessment tools, and ways that hot water can interact with the grid to help us get to net zero. And for anyone that wants to know more, we've been pulling together all of this knowledge sharing and things from the task on our website. There's a link there. And so far we only have 2 of our 8 planned reports published, but I've seen that these drafts are getting finalized, and we should have quite a bit more available in the next few months. So that's the overview from my side. I guess we'll probably reserve questions until the end.
But
right,
Robert,
Beryl? Yeah.
before you stop
Yeah.
sharing, go back to, I think it was slide 5, because there's a direction question to this very interesting craft, and we can show it again. This one, exactly.
Yes.
Because there's the question why there is this drop in the MENA region at the end 2023. And you might not know it, but I just looked it up in the report while you were speaking. And this has to do with reporting of figures, you know. So it's not a market drop, but you know that the country, the INTech team is always depending on that countries send market figures back. And the growth, which you see there, or the rather, well, stable MENA region development was mainly because of Lebanon and Palestine. And you can imagine that from this instabilized region, there were no figures reported in 2023. So that's why there is a drop there. So that's the background of the drop. So this was only directly related to your presentation. Thanks, Robert.
Yeah.
Perfect. But we will go
Yeah,
on
and
with
I should
okay.
mention we have one of our task leaders is also involved in the Solar Heat Worldwide report. So there's a good link with that Solar Heat Worldwide report there.
Yeah.
But yeah, I'll stop sharing and we can move on to the next
Exactly.
presentation.
Yes. Perfect. Thank you. I will share my screen and present our next speaker, which is actually from China. Let me see. That's it, I hope. Yes. We go to the next slide. Yes. So we have Dr. Borja Li with us. He is also professor at the Solar Energy Application Center for the China Academy of Building Research. His research mainly focuses on the solar thermal application and energy efficiency technologies in buildings. He holds a PhD in HVAC from the Tianjin University, and he is contributing to the National Key R&D program, which is called Key Technologies and Demonstration on Zero Carbon Building in Solar Energy-Rich Regions. And he has actually a long title of his presentation today. He will talk about global warming potential emission reduction testing in China for thermosiphon systems. So, Borja, the floor is yours, and I'm looking forward to your presentation, and stop sharing.
Thank you. And I will share my slides. Okay.
Yes.
Okay.
Yeah.
So maybe
Perfect.
there are some small mistake. My presentation title is green house
okay.
gas emission reduction testing for thermosiphon systems in China. And I'm Li Bojia from China Academy of Building Research. I just Bubble and Robert introduced, and I joined the IEA SHC Task 69. I'm the subtask leader of the subtask B for thermosiphon systems. Today, I want to share one of the important output from the subtask B, and the title is about the emission reduction testing for thermosiphon systems in China. And next, there are 4 main parts of my presentation. First, for the subtask B. The subtask B is mainly focused on the thermosiphon systems. Although now the thermosiphon systems market mainly dropped down in most of the market in the whole world, but they still represent the majority of installed solar hot water systems. And through this subtask, we want to promote the thermosiphon systems in the whole market. And we want to buy 3 methods. First is about to investigate the new systems about improving the convenience and performance to get a better design or management technologies. Until now, we gathered a lot of interesting new innovation on thermosiphon systems, such as smart control systems, cloud maintenance systems, and new material for thermosiphon systems. they will all gathered in our deliverable V1. And the second is second goal is to investigate from the failure modes and effects in different regions, mainly is in the Africa countries, and to find the way to improving durability and reliability. And the main failure modes and effects are already present in last Solar Academy. So today I want to share the third one is to investigate the energy saving and emission reduction performance of thermosiphon systems. We want to we want to know how we want to tell the whole public how the thermosiphon systems contribute to carbon peak and carbon neutral goal. And we want to attract more attention from society to tell them we are doing a lot contribution to carbon emission reduction. So that's our initial motivate for our this subtask and for our this part of research. The background is China accounts for about 73% of world's total installed solar collectors, and the as I just told, the thermosiphon systems or the solar hot water systems is making significant contribution to energy saving and carbon reduction in China. But it's very hard to calculate solar hot water systems contribution to carbon neutral goal. That is because now China lacks emission reduction assessment method for solar hot water systems. There are China's own certified emission reduction methods, but only 4 methods published. One is about solar thermal power generation. Others is about carbon sink for forest and grid-connected offshore wind power generation, and mangrove forest construction. None of them relevant with solar hot water systems. And for the international method, there are clean development mechanism. This is main developed by United Nations, and there are one method is for solar water heating system, and the method including 3 ways. First is system simulation, second is system metering, and third one is stipulated energy saving. They give a constant annual solar yield for solar hot water systems is about 450 kilowatts hour per square meter collectors. And we think maybe this method is also not quite suitable for Chinese situation, because there is a lot of difference between China and Europe and US in hot water systems, and that may cause difference in the emission reduction. For example, China have a lot of different cities. They have a lot of different, very different solar resources. For example, in Beijing, and the solar irradiation, the annual solar irradiation is about 1,000 and is about 1,500 kilowatts hour per square meter. But in Tibet, there may be more than 2,000 or even 3,000 kilowatts hour per square meter solar irradiation. So the solar resource is very different in different place. That means you will get different, very different emission reduction with same solar thermosiphon systems. And other is a system type. In China, this compact system it take the majority in the thermosiphon systems. This is use evacuate tubes and water tank. They integrated them together to provide hot water. And the hot water demand is very different because a lot of high-rise department building in China, and the government used to force building to install solar hot water systems. So you can see a lot of this type is flat plate balcony system and installed in the high-rise department buildings. Therefore, we think other countries' experience maybe is not quite suitable for emission reduction in China. So we start our research and we want to build a method to calculate, to assess the carbon emission reduction for solar hot water systems and tell the public how much carbon emission reduction the solar hot water system could provide for the society. To ensure the reliability of the method, the research include this maybe 4 parts. First, we generate a main procedure to evaluate the emission reduction performance for solar hot water systems. We already know the ISO 9459 Part 2 gave the testing method and long-term calculation methods for solar hot water systems, solar yield. For example, we can calculate one solar thermosiphon systems could get how much solar yield through 1 year. Then we could convert them into carbon reduction by plus carbon factor. I will talk about it later. And then we make long-term modeling. We have a model annual energy saving and carbon reduction by daily calculation. And this method, this modeling procedure is mainly followed the way used in ISO 9459 Part 2, but we make a little adjustment to make it suitable for the compact system I just said, the most popular system in China. And then we did a long-term testing and to verify the model with operation data. And then we we do the simulations for solar hot water systems in different cities in China, because China has a lot of different cities with quite different solar laws. And then we reach the total emission reduction for solar hot water systems in China. And the general procedure is mainly 3 procedure. First, for the individual samples of solar thermosiphon systems, they should be testing in laboratory according to ISO 9459 Part 2 and Chinese standard, national standard 18708. And to get the main characters of the system, mainly about the solar yield and heat losses and the drain water temperature curve. There are a little difference I just told is for the compact system in China. It's a open loop system. So the drain water temperature, when you drain out the temperature, when you drain out the water from the tank, the temperature remains same, and as no cold water will be added. And so you could only drain out about 1 times of the tank volume water during this step. So we took these 2 standard. This is for the compact systems. This is for other types of system to get this. And then we calculate annual energy output and saving with the software, because we must get the annual energy output through the daily calculation. We calculate everyday solar yield and everyday heat losses, and we give a daily water use curve to simulate the water usage. And maybe the method is very similar to ISO 9459 Part 2, but the calculation, maybe you have to calculate 365 times a year. So we developed a small software and to make it easier. And then when you get the annual energy saving, annual solar yield, you could convert annual energy output to carbon reduction. We in this stage we in the research we use electric water heater and gas boiler as a reference systems. But for the testing we use electric water heater as a reference system, and then the carbon emission factor of electricity power is used to calculate the carbon reduction. And I will talk it later in detail. For the initial parameters, as I just told, there are these key parameters and could be tested in laboratory according to ISO 959 and one Chinese national standard 18708. And then you can get these characters, and then you could input into our testing model. We make a small calculation software, and you input that. The software will calculate the whole annual solar yield and carbon reduction automatically. This is the main calculation procedure. I think it depends on the time. I don't have enough time to introduce in detail, but maybe you could look that later. And for the convert to carbon reduction stage, as I just told, the emission reduction of solar hot water systems could be calculated with following equation. It's mainly about the generally it's about the baseline emission and divide to the projected emission, and for the if you have the testing or calculation solar yield per year, you could plus the baseline carbon factor and then divide the baseline efficiency. That means the efficiency means the electric water heater or gas boiler, the energy efficiency. According to Chinese national standards, the energy efficiency for electric water heater must be no less than 0.95, and for the gas-fired boiler must be no less than 0.86. And for the carbon factor for electricity, we usually use 0.5 kilowatts carbon dioxide per kilowatt hour. That is our government announced the electricity carbon factor every year, and we could see last year is about 0.56, and the year before last year is about 0.58, and now it's declining every year. We did a prediction for the future 5 years carbon factor, and then the average one is about 0.5 kilogram carbon dioxide per kilowatt hour. Usually we use this figure to calculate the carbon emission in Chinese national standard. And for the gas, maybe this is more fixed. and it's about 0.2 kilowatts, a kilogram carbon dioxide per kilowatt hour heat. And okay, that's all the assessment method part. And then to verify the calculation model and the calculation procedure, we built a carbon reduction testing field in Jiangsu province with the help of Solar East company. And this also a part of the output from our subtask B. And this is a view of the testing field. There are 25 types of solar thermal systems, and maybe not only solar thermal systems, all the thermal systems have been installed for long-term testing, including the solar hot water systems, and also including the PV water heater and PVT systems and some heat pump systems. But we only use the solar hot water systems for verification. We mainly use these two kind of the system. One is the compact system or open loop system, or this is the most popular system in China. There are 10 samples have been tested, and the average daily energy saving is about 2 to 4.7 million joules per square meters. And the average daily emission reduction is about 0.33 to 0.75. And for this type is most popular system in Chinese high-rise department buildings is a balcony system. This type of system is pressured system and is closed loop system. This is a tank. This is a flat plate collector. Maybe this will be usually this will be installed outside the balcony and with a pipe between the tank and the collector and connected them to transfer the heating fluid. And there are about five systems have been tested, and the average daily energy saving is about 0.8 to 2.3, and the emission reduction is about 0.14 to 0.5. And this you could see the pressured system or the balcony system is less than the compact system. That is because this is mainly designed for balcony for high-rise building, and the slope of the collector is not quite good as the compact system. And then for the verification, we input measured solar irradiation weather data and system parameters. Sorry, to the software we developed, and we compared the calculated solar yield and the tested solar yield, and we could see the deviation is about 10%. We think our method is accurate enough for evaluate the individual thermosiphon systems emission reduction. Sorry, I will be quick. And then with the method, we calculate 34 cities in China, and to calculate the thermosiphon systems carbon emission contribution. And this is a location of these 34 cities. And this is a result. We could see the cities located in different provinces and have the different solar energy resources. The extremely rich resources is about more than 7,000 million joules per square meter per year. And the worst solar energy resource is about Chongqing. They have about only 3,000 million joules per square meter per year. And it's less than half of the Lhasa in Tibet. And when we get the solar yield and emission reduction for each city or each region, we think this city could, on behalf of this province, and to get a average figure for the whole country, we think we use this figure weighted according to the population of each province. That is, we think in China, almost every family have thermal phone systems. So maybe the people, the city with more people, the thermal phone systems will be more. So that will be reflect the how many the system have been installed, and then we get the final figure, the average solar yield for some cell phone systems in China is about 420 kilowatts-hour per square meter, maybe less than the figure in CDM method. And the average generation, average emission reduction is about 97 to 220, because this figure is different because this is compared with gas boiler. This figure is the reference system is electricity because of the because China, because we can see the electricity has larger carbon factor compared with gas boiler. And then if we take the solar heat worldwide figure into calculation, the total annual emission reduction is about 50 to 120 million tons of carbon dioxide in China. So the Chinese solar thermal systems now is contribution about 1% of the Chinese total emission now, and we think this could tell the society our solar thermal is contributing a lot to the carbon neutral goals. Okay, and all the method I told is now support Chinese national standard for carbon emission reduction assessment of solar thermal systems. And now, and also the English version is available. And the other day, Babo asked me if there is a link we could share this document, but unfortunately, this document have not be open to public. If there if they could be open for public, I will share the link in the future. Okay, I think the time is up now to give a summary. Due to different solar resources, the systems and hot water demand profile is necessary to development assessment method for emission reduction of solar hot water systems in China. And we developed the method for the annual energy saving and emission reduction based on daily calculation. And a testing center has been established and verified our model. And the reference value of emission reduction of systems have been proposed through this assessment method research. And this will support our emission reduction assessment in solar thermal industry and development for future. And that's my presentation. Sorry for the time
Yes, 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 that's
control.
it.
Sorry, very
If
sorry.
Thank you very much for the
Okay.
interesting talk. Yeah, if you invite professors, you have long speeches. That's clear. But it was very interesting into this insight, what China really contributes. And I think it's important to really figure out this contribution as you are the largest market, solar thermal market worldwide. Good. That brings us, sorry for the questions, but we will have enough time at the end for the Q&A. So I will hand over to our next speaker, which will be Tony Day from United Kingdom. And I will share again my screen to introduce you properly. Voila. Oh, this is the beginning. Not really. Oh, here we go. So Tony Day, he has an interesting career actually. He's an independent consultant specializing in leading edge of energy systems research and policy development. Previously, he served as the director of the International Energy Research Center, which was established to develop academic industry partnerships for near-market energy solutions. Prior again to joining the center, Tony had worked 20 years he has 20 years of academic experience in research, teaching, and consultancy of energy efficient buildings, low carbon technologies, and energy policies at London South Bank University. So an interesting mix of research industry background from Tony, and he will give us an insight now into PV hot water configurations, opportunities, barriers, and policy needs. So Tony, you are British, you can speak fast, and you save us some time now. I'm looking forward to your presentation.
I will see what I can do. Thank you, Barbara.
Whoops.
Can you see my screen okay?
Looks great. Yes.
Thank you very much. Okay, so I'm a mechanical engineer by background, building services engineer, but and like many people, when I came to this subject of PV hot water technologies, I was dubious because it's an emerging technology, but I think it's had a history of people seeing it as a very poor use of electricity to heat water. Thermodynamically, those thermodynamicists amongst us will know that heating water from electricity is seen as a bit of a no-no. However, there is this emergence of this technology of using PV electricity directly for hot water for a number of reasons, and these are the drivers. I mean, solar PV hardware, particularly in the last decade, has seen a huge reduction in cost, and it's become very affordable, as Robert said in his introduction. It's a very flexible technology, so you have multiple applications. So there are many ways in which you can use this according to need, to climate, to cost, etc. Smart control systems are now becoming much smarter. We've been talking about smart control systems for a very long time, but they are now truly becoming much more intelligent, and we can start to optimize PV generation and actually play tunes with different multivalent systems using smart systems. Some countries have a very strong electrification of heat policy. So these strategies for driving electrification of heat is happening largely because we see the decarbonisation of electricity grids. And that's particularly true in Europe, where of course I am, and in the UK. And we've seen the electricity grid decarbonise from 900 grams per kilowatt hour 30 years ago down to under 100 grams per kilowatt hour now. So that electrification of heat, it says, well, we should actually be using electricity for heat. And that means that you now have some value for thermal storage of using thermal storage for electricity load management. And there's some real value in that. We'll talk about that. And things like time of use tariffs. We have pricing signals now that can actually drive people to change their behaviors on how they would utilize electricity. And there are policy measures that are coming up to encourage the uptake. So the task, this is subtask C for the task. And we've already had one publication, and I would advise you to go and have a look at this. There's a link there for this publication, which tells you a little bit about the technologies and the opportunities around the technologies. It's supported by some research journal papers that you can see there, and they're all very very good pieces of research. And in progress, we have a piece of work on policy initiatives around the world for PV hot water. And as it's an emerging technology, it's not surprising that there are not many existing policy initiatives. So that piece of work is actually in its first early draft stages right now. So what are these different applications? Well, we can actually just take, in its simplest form, we can say PV electricity from a photovoltaic system on your roof and just put it straight into the hot water tank, an electric immersion heater, and heat hot water directly from PV. And in its simplest form, that's a very cheap and simple way of doing it. That's a direct competition with the kind of systems that we've heard from Borgia just now, from thermosiphon or even pumped solar thermal systems. So that competition is an interesting one. The next application is PV self-consumption for hot water. So if you have rooftop solar, you're generally using that either for powering appliances in the house, or you might be exporting that to the grid at certain times of peak solar output and low use. But you can actually divert that electricity into your hot water tank if it's more valuable to do that than to export it to the grid. And that all depends on the prices on the electricity grid and what you're paid for exporting, which most often is very, very low. And then finally, this idea of hot water from grid PV. So we're now seeing a large growth in some countries of grid-connected PV systems, and I'll talk about this a little bit later on. And there are options and possibilities for centralized switching of residential water heaters, so you can actually divert electricity into the residential hot water tanks. So you've actually got a large thermal battery that you can start playing with for grid management, and we'll see why that's important. So where is this going to happen? Well, those different applications will be different for the different circumstances. So, for example, where you have high solar uptake at the moment, those areas in dark red have the highest per capita solar uptake around the world, and so there are huge opportunities. This is PV uptake. So there are huge opportunities where you have a large amount of rooftop systems of saying, well, why can't we just use that electricity? If we have excess electricity, maybe we should use that for heating hot water. So that's one option. But then there are the other circumstances that there are a number of countries around the world where grid electricity is perhaps less reliable, less stable, and it makes less sense to have an interconnected grid system with your PV rooftop, and you may have much more autonomous systems. In which case, you want to heat your hot water directly, or you might want to heat hot water and domestic appliances, in which case you need to go for smarter systems. So in some cases, some of these countries, they overlap those two different types of markets. So it's a complex situation of where PV can work. So we'll get a brief look at those technologies. PV to heat. There are growth markets in these high cost grid connection areas. So for example, Southern Africa, there's an example here from South Africa, and you can see some houses there that just look like ordinary PV systems, but they are connected directly to hot water tanks, and they generate the hot water instead of having solar thermal systems to do that. And we can see that there's been a big growth in those kind of systems in Southern Africa. This technology is still developing because you want the most efficient system. So, for example, having maximum power point tracking, that's necessary to properly match the output variable output of the PV depending on the solar radiation available, and match that to the optimum requirement of the heater elements. So these systems need to be a little bit smarter than just have an inverter and or even direct current into the resistance heating. So the other option here, where the electricity markets are probably more stable grids, more mature electricity grids. So, for example, in the UK, we may have hot water storage. It's grid connected, PV on the roof, and we will decide whether we're going to use the electricity from that PV to run our appliances, to export from the grid, or if we have surplus, we can divert that to the hot water storage tank. There is a big resistance in countries such as the UK to do that, where we typically heat our hot water from natural gas systems, and the idea of where gas is so much cheaper than electricity. So you would need an additional system if you're going to have PV diverters to heat the hot water tank. Well, it's not such a problem, because all of those gas water tanks will generally have a backup electric immersion heater. So it's actually very easy to fit these PV diverters into existing systems, and right across Europe, that's where the market is, and also in Australia, that's where the market is for these kind of technologies. This example that I put here of Mixergy, the company Mixergy, in fact, go one step further, and they have a smart hot water tank that can actually manage the state of thermal charge of the tank. So you can actually start to optimize whether your electricity goes into the tank, to the grid, or into the house, and how much hot water you're likely to need in the coming hours, and you can start to have much smarter control. So that's a really interesting adaptation of these technologies, and making them much more attractive where you have growth of PV systems. So in the UK, we don't have solar thermal systems, so we have a lot of growth in rooftop solar PV, and so there is now a lot of interest in having these smart control systems that can manage the way that we generate and value the electricity from that PV system. We can have the PV output to drive heat pumps, and in Germany there is a growth in that market. We haven't seen it, for example, in the UK. It is more sophisticated to do that, and generally you need a good amount of solar radiation year round to enable that to become much more cost effective. In the UK and Ireland, where it's cloudy most of the winter, that's not a very effective solution necessarily. And then we come grid PV to heat. And this is a really interesting issue that is becoming apparent to a number of countries right now. So Australia, where there is a high amount of PV rooftop market penetration, there is also a large amount of solar grid PV as well. And these things can be in competition, because the solar rooftops are taking load, they're taking business away from the centralized grid. And this is also beginning to happen in the UK. The graph on the top right is some modeling that I've done that shows solar output in the UK falls far short of energy needs. The blue is the energy demand in the UK. But in the summer, if we put in 45 gigawatts of solar, which is the target in the UK, we will have excess solar capacity on the grid. What are we going to do with that? Well, maybe we need to start diverting that into a typically non-electricity demand, which would be hot water. So these technologies that are actually start to require a little bit more interaction between the grid and the domestic end user. So as I say, in Australia, this is particularly an issue. Robert mentioned a bit earlier that at times the price of electricity on the grid can go negative when there's too much solar on the system. So there are trials there to say, well, can we actually use this large thermal storage battery and control that in a smart way centrally? So these trials are ongoing. Right at the beginning, we asked the experts in the task what they thought the market potential in this area was. There were 42 respondents. It wasn't a huge number of people, but you can see medium to high growth potential was seen by a lot of these actors, and these are academics and commercial actors in the market. So yes, they would say they see potential here. I think that if we ran that survey again now, we would see more respondents because more people are interested, and I would actually see that high growth potential become a larger share. So the outlook looks positive for PV to heat. There are a number of barriers, system costs, and there's not enough skills and knowledge. And that's one of the things that obviously these tasks try to do, is to improve our knowledge in these areas. The technology competition, where does this compete, for example, with solar thermal? What is that an issue? And how the markets around the world going to mature? And there's a significant lack of regulation and a lack of understanding at the policy level. So we have these market drivers, which are around operational savings. These PV diverters can actually optimize the value of self-generated electricity. And the grid scale control can use these thermal batteries to actually avoid curtailment, which adds cost to the whole network system. It can reduce these peak time demands and actually can help to make the system more efficient. We can have system balancing and quality control. These high numbers of distributed PV systems, they can cause system security issues. And we've seen that, for example, in Spain on the Iberian Peninsula, where we've seen some grid stability issues. And we want to make sure that we have good quality electricity on the system at these high penetration rates. And some regions actually will use kill switches to say, right, there's too much PV being generated on people's roofs, so we've got to switch you off. Well, rather than do that, it would be better that those end users can utilize that electricity themselves by diverting it into a useful application. So the perceptions are PV has not been seen as a hot water heating technology prior to this, and the competition for high efficiency solar, particularly in the Sunbelt regions, often rule it out, and probably still now. Direct electricity is higher in cost than fossil fuel heating in the temperate regions, so that it has to overcome that barrier. And there's a lot of engineering resistance, that thermodynamic resistance to say low entropy energy for high entropy end use is a bad thing to do. And the cost reductions of rapid PV deployment actually are now changing the market dynamics. So things are moving. And one of the things that we're really interested in is how the policy and regulation space needs to actually keep up with the pace of change of technology. And I said earlier on, we're now undertaking a piece of work to understand what that policy landscape looks like. It's actually very difficult to identify specific PV to hot water regulation, but actually buried in a lot of, so in the UK, buried in the new forthcoming building regulations, for example, it will be very difficult to actually meet those regulations if you don't put in systems that have zero carbon hot water heating strategies. And in the UK, that will probably have to be PV. So these technologies may, in some markets, actually become almost mandatory. So currently the evidence, it's limited around what policy instruments and regulatory instruments there are out there. But there are a number of them, as I say, they're buried within renewable energy mandates, and that needs to be brought out, and for policymakers to understand the opportunities. So we see PV hot water systems, they're seeing significant growth. The application and uptake, they depend on climate, the electricity system maturity, and the PV market penetration rates around the world. So PV hot water can be lower cost than solar thermal, because of that reduction in hardware price. And the advantages for reducing the operational costs for residential PV owners, I think, are becoming pretty evident. And it may have significant role for this grid balancing and security and operating costs that I mentioned. And what we really need is clearer regulation to fully unlock that market potential. So that's a rapid run through this emerging PV to hot water.
Excellent, Tony. This was a complete shift away from thermosiphon traditional markets to modern smart PV to heat markets in UK.
Yeah.
So thank you all together, and bring up your cameras now. We start with the Q&A, and we have some really challenging questions. And I would like to start with the more general ones. And this was one of the latest ones asking us for whether you have ever done a calculation on the carbon footprint of PV and solar thermal. Was there anything done in task 69?
Shall I start?
Yeah, sure.
Well, not directly for PV hot water systems, but I do think that this area, because it's fast moving, may well be a need for future research to actually understand what those full life cycle carbon issues are.
But not yet done. Okay. So
Can I add one thing?
yes, sure.
So of course, there's quite a range of the PV hot water technologies. I think the one where you just have PV, a little bit of electronics, maximum power point tracker kind of thing, and then direct to a resistance heater, that's pretty low carbon emissions. I mean, that's got to be competitive or better than a thermosiphon system. But of course, if you start adding in a heat pump and a bunch of other moving parts and smart tank and all kinds of stuff, then it's gonna be take longer to pay back. It's embodied carbon and all those bits of equipment.
Maybe we stay there for a moment. Tony, do you have an idea on penetrations on such PV consumption, solar water heater solutions? Like you have talking about Mixer G or something. You have ideas of penetration rates in the UK?
I don't have those figures to hand. I think we did. I'm not sure some numbers went into solar heat worldwide, but there are some companies, for example, My Energy in the UK produce these PV hot water diverters, and they have a very healthy market, I think. I don't know what the numbers are, but it's certainly seeing growth. Mixergy are certainly seeing growth. That started from a small base. The idea of a smart hot water tank is still catching on, I think, in the UK. Probably it's an export market for them at the moment. It's still small, but I think because the value of PV electricity is becoming much more recognized, that we need to do more with it, that it's almost inevitable that these systems are going to take off, I think.
But what is their back charge in winter, the backup? Because I mean, they must have a backup because PV cannot provide them all the year round.
Oh yeah, so
They
in winter you can use either the grid.
the grid.
Or these systems can be multivalent. So you might have PV rooftop and a gas boiler. So it might be you've got gas heating, but with a heating element. So something like the smart Mixergy tank can decide: am I going to switch on the boiler? Am I going to use, because the sun's out now? Am I going to use this? What's the price of electricity on the grid? Can I export it? So those kind of decision making has to happen with a smart controller.
Smart meter. Okay.
Yeah.
Okay.
Or it could be with a heat pump. So that's the other component. An all electric house with the grid, with PV on the roof and a heat pump, in which case you're getting the benefit of the heat pump COP. My house, my heat pump only 2 kilowatt hours a day required. So actually, that could you could get that in some of the winter as well.
Yeah. Borja, there were some interesting questions about your closed loop and your open loop systems. Maybe you explain first the difference between the two. What do you consider as open and what do you consider as closed?
The first about the open and closed, I think is about the water supply system, and for the compacted system or the open system, the the tank must be installed in a higher place as the water will supply directly into the tank, and when you use the hot water, you could open. And there is another pipe from the tank to the tap for the users. And when you open that, the tank is direct open to the atmosphere, so the water will drain, hot water will drain out, and without no pump, without pump, and without new water, new cold water supply. And for the closed system, the main difference is about tank could be installed, for example, in the balcony, not maybe not in the highest place in the whole system. And like the electricity, hot water heater in everybody's home, and the tank is closed, and you must have cold water add in, and to put the hot water go out through the from the tank. That's the main difference.
That's the main difference. So in your presentation, it looked like the closed systems had lower performance than the open systems. Why is that?
In my opinion, I think there are three reasons. The first is the collector slope, and because the closed system is mainly used on the in the high-rise department buildings. So the collector installed on the outside of the balcony. Maybe this convert, they will install convert or nearly convert. The vertical or nearly vertical installed on the building surface.
Ah, okay.
But the compact system, they will installed on the rooftop, and the slope will be more suitable to gather more solar irradiation. The second reason maybe is about the heat transfer, because the closed system use antifreezing fluid to transfer heat from collector to tank, and there will be a heat exchanger inside
And
the
some
tank.
losses.
So that may cause some losses. And third one is they use flat plate collector. As our testing results, according to our testing result from our laboratory, and usually the flat plate collector has larger heat loss coefficient. So that means it will lose more heat through this collector. And I think that's the three reasons.
These are the three reasons. And then you have shown these big tables in your presentation where the different systems were lined, and somebody wants to know whether there it was rather flat plate collectors or rather vacuum tube collectors, or it was a mix.
It's a mix.
It's a
because
mix.
we
Okay.
don't have the data about the market share in different cities, so we use the average market share in the whole country to
Okay.
get the mix.
So that was a mix of different regions. And the last question to you is about the developed software. Was this also tested in the MENA region, or could you transfer your results to the MENA region?
First, I must say it haven't been tested in other countries. But I think I'm a little confidence, or maybe lot confident, lots of confidence for it could be used in other countries. Because this software could use weather files, other countries' weather files, other countries' water usage profiles. So it could the basic method or the basic procedure could transfer to other countries, but we must use the other countries' weather file and water usage profile and the carbon factor also. Maybe that could be make it use
Okay.
in other countries.
Okay, thank you. Great. Then there was a question on whether there was a direct comparison made in the task between a solar thermosiphon system and an electric one with PV. I think you mentioned the one in Namibia, Robert, and maybe Tony, if you have anything heard from UK. What are the results in Namibia, the preliminary results from there?
Yeah, so the results are just coming in now. Of course, we visited the site and they have a little bit of data, but I don't think they have a full season worth of data yet to make any conclusive results. But that's definitely one of the things that we'd like to have, and that's coming up hopefully within our task by the end of we'll have some report on that.
So that there will be a particular report on this comparison, or it will be part of one of the reports?
Yes, if they get data in time. Of course, our task is finishing at the end of the year. So, I assume that test needs a full year of data before you can really come to any conclusions.
Okay. Tony, have you heard of such comparisons in the UK?
Not in the UK. Very little work goes on in solar thermal in the UK. So any of the solar manufacturers in the UK will most of their work would be done in Spain or other sunnier climates. So that comparison's not been done here. So PV to hot water would be really compared against its advantages against gas boilers or heat pumps or those opportunities or the grid.
So this was again one of the questions actually, why solar thermal is on the back foot of the UK, is respectively has a higher efficiency than PV.
Yeah, it's interesting. I used to have before I moved here, my last house when I moved in there sort of 25 years ago, I put solar thermal on the roof. I felt I had to as a building services engineer who was researching and teaching renewable energy. I put them on the roof. I mean the payback, and these were just flat plates. The system was very simple. The payback was still very long. I probably never actually. It wasn't very expensive. It was maybe £2,500 to put that on the roof, and I moved out of that house after 20 years, and I probably hadn't actually paid the money back because gas prices are so low that the and you use your hot water load is less than £50, £100 a year or whatever. So it wasn't a huge saving. So in the UK, the solar thermal market has never taken off. And when the government had renewable energy subsidy packages for renewable technologies, solar thermal really didn't get a look in. And so we used to have a thing called the renewable heat incentive. And although solar thermal was mentioned, the government did not encourage paying people for solar thermal heat. We just don't have enough sunshine here. It's interesting, when I worked in Ireland, I saw more solar thermal collectors in Ireland, where it actually is even cloudier than UK. But but PV on the other hand has really taken off here.
Okay. Well, I think there's a nice suggestion from one of our participants, Mohammed Ali Jafar. He's asking for a list of advantages and inconveniences when you compare the two technologies, thermosiphon and PV. And as you are still writing on your reports of Task 69, maybe this would be a good one. I think you have touched upon in some of your presentations, but it would be good to have this a bit more systematic. Maybe we give you the floor once to you, Robert, because you are really joining us from Australia, and Australia has this enormous amount of rooftop PV and also a picking up option for PV to heat. How does it look like with smart companies like Tony mentioned? Do you have such smart boiler providers already that use this surplus electricity from the roof?
Yeah, so I think Tony mentioned it, but I can say a little bit more about it. So of course, when coal was being generated, is our main source of electricity, people had to do things to make sure that the coal power plants didn't have to turn off at night. One of the things they did was connect a bunch of hot water systems, and they have these controlled loads where they can turn on your hot water system for you to soak up some of that coal electricity. Also, street lights suck up the coal electricity. But now, as we get PV on the grid, we have to think of some ways we can suck up and soak up some of that PV electricity during the middle of the day instead of at night. Right. And so it's the same stuff. You have a controlled aggregated systems of hot water systems, or maybe other household heating and cooling technologies that can take up that excess solar energy. And it's just a really cheap form of energy storage if you think about it. And so one thing in Australia that's happening is they're starting to curtail. That means just turn off PV modules. And it turns out the amount that's been curtailed is about the exact same demand as we have for hot water. So if we could just, instead of curtailing it, put it into the hot water systems, we'd be sweet, right? We'd have all of our needs met from solar there. And so that's an interesting thing. And then it also brings up another point of aggregating systems. So if you have these, heat pumps with all the bells and whistles, they can talk to each other, and some central aggregator can turn them on and off as the grid needs. And you can provide ancillary services. I'm not an electrical engineer, but there's a lot of value in that. The electrical engineers tell me for those frequency control things and some other things that hot water can actually do, which you don't think about something like hot water doing that, but it can really help balance the grid. Another thing that's interesting comparing the thermosiphon and the PV is cold climates. So, we've got ways to deal with cold climates for thermosiphons. You use, I think Lee mentioned using some kind of glycol mixture or something that doesn't freeze, or draining the systems. But of course, PV doesn't care if it's out in freezing weather. Of course, if it gets snow or ice on it, it'll have limited solar, but it doesn't freeze, and it doesn't care about cold weather as much, and it can stay reliable in those cold climates. And so some interesting advantages for cold climates as well for that comparison. So there's a lot of interesting things, but we can't forget about thermosiphons. Thermosiphons are still really efficient, you can get above 50% efficiency. So
for the last 2 minutes.
So they're both gonna be something.
You have to write this down in one of your reports systematically. But we have seems that we have participants from India and very southern countries, and they ask us again, can you give a quote for what is a good direction for India, for example, rather go thermosiphon or go to PV to heat? What would be your suggestion? Like you have been in Namibia as well, which is also a southern global south country.
Well, I think looking at Tony's map, India was one of those places perhaps where there's unreliable grid in some parts, especially more rural parts. Obviously, like major cities, it's not a big deal anymore, but more rural areas, you basically got two choices, right? You can do thermosiphons or this PV technologies. And India doesn't have a freezing problem. So then it just comes down to cost. So I guess one of the nice things about thermosiphons and solar thermal is it can be locally manufactured. Some local manufacturing is possible. PV, it's pretty tough to locally manufacture the PV modules. Of course, the hot water tanks and the heating elements and everything can easily be locally manufactured. China's got most of the PV market. Maybe India's getting more PV manufacturing, I don't know, but there's a lot of trade-offs, and they're pretty competitive, I think, thermosiphons and PV hot water in some of those places. So it really just comes down to the costs. Yeah.
Okay.
Yeah.
Good. Well, last one, but probably difficult to. Was there any leverage carbon credit or financing mechanisms that you hear of, how developing countries could profit from subsidies while establishing solar for hot water? Have you ever heard that?
Yeah, so most of these things are national schemes where you get some kind of rebates or
Direct.
tax
This,
things. I can't speak to every country what they have in there. So that's the carrot. There's also sticks of building codes, I think Tony mentioned, where
yeah.
you have to do this, some regulation that forces you to do it. Or I think in China they had forced every new building needs to have solar thermal on it. And so there's some sticks and carrots. And there's also some companies around the world that pay for carbon offsets that you might be able to tap into.
I think that was mentioned there. That was asked
Yeah.
for, yeah. But you have not particularly looked into that.
So we haven't done that in our task, but you know, a lot of major companies around the world, even like tech companies, are trying to be carbon neutral, and the only way they're going to really get there is by buying offsets. So if you can provide some offsets for them at a reasonable price, it's hard to compete with planting a tree or something, but solar technology is going to be more expensive than that. But yeah, maybe, and then I think Tony was going to say something on this probably too.
Tony, you get the last word now.
Well, I think Robert actually covered it, but I mean, I think we've seen these financial instruments being withdrawn in some countries. So in the UK, we had subsidies, and as the price came down, they've been withdrawn. So but they still exist around the world in different markets where you know the capital cost is still an issue, but because it's coming down very quickly, the PV issue that's can outcompete thermosiphon systems on cost. So those subsidies can start to be withdrawn, and where that happens, I mean, renewables are now competing very well with fossil fuels and on price. So we'll see fewer and fewer of these subsidies, but I think more about regulation so that you can apply it in the right way. And we're seeing offsets slightly discredited now. I think the value of some of these offsets schemes has been called into question. So yeah, I'm not aware of any that directly would tap into this potential market. But it is an idea because they would be real carbon offsets.
Okay. Good. This was a very interesting Q&A. Thank you so much for all the interesting input. I will hand over back to Arabella for the last final words on this webinar.
All right. Thank you very much, Bärbel. And thank you, of course, to the speakers for their presentations and the audience for your lively questions. There was quite a lot that came in. To wrap things up, we have recorded today's session and we will make the recording available to you on the ISIS YouTube channel and also on the IEA SHC Solar Academy homepage. Also, the same goes for the presentations that you have seen. They will be made available as PDFs. You can kind of go back and browse through. Yeah, and that's it for today. We are looking forward to meeting you on the next webinar and see you soon. Thank you, everybody. Bye.
Bye. Have a great afternoon.
Bye.